I got sick because my marker didn't paint. I was talking about the the heat, the changing temperature, but of an object with a mass. So it's given by delta T equals Q over the mass times the specific heat of the object. So we here, let's suppose that we have the heat is 51.7 joules, the mass is equal to 5 kilograms, and the specific heat is going to be given by, let's suppose that this object, we have a ball of aluminum, but I'm going to invent this, so let's suppose that the specific heat of aluminum is of 5.47 joules over mass times degrees. So we need to substitute this here, so the change in temperature is going to be given by the heat, which is 51.7 over the mass, which is 5 kilograms. Sorry, this is times 5.47 joules over kilograms over C. So the joules and the joules are going to be cancelled, kilograms and the kilograms, and delta T is going to be given in degrees Celsius. This is for a case when an object, the change in temperature of an object that is receiving certain heat and it's having a mass, and you have an object of a defined material. So in this case it was aluminum. Now I'm going to talk about the energy to melt a solid. The energy to melt a solid, we know that where we have a solid, let's suppose that we have a cube of ice. Where we have these particles so tight between each other. So we need to apply heat in order for the bonds of the particles to be dissolved and to have now, instead of two particles together, to have particle 1 and particle 2. But this for the whole body. So the energy to melt the solid, this was energy, sorry. The energy to melt the solid is going to be known as the latent fusion. It is a specific heat and a specific type of energy. Well, it's also given in joules, but it's a specific for each material also. So we have let's suppose again aluminum, that the latent fusion heat is going to be given at a certain number. That number is going to be the energy required to melt a certain quantity of aluminum. So if you have a problem of this, you need to make the proper calculations to make for the whole body. Also, there is where we have, we're at our house. Let's suppose that Coco is at his house. And he is about to bake. And let's suppose we have a pot here filled with water, and the heat is increasing. So at a certain point, the molecules here are close together, but not that much. They can move freely, and they don't have a certain volume. The volume is adapted to the container. So there is energy called the energy of vaporization. To make if this is the energy we need to apply to the water in this case, for the water to get vaporized and change into vapor. Also, in temperature, it is known as the boiling temperature. Now finally, we can think of a bar with a transverse section A placed in between a thermic deposit at a temperature Tn and a thermic deposit with temperature Tc. Let's have a bar here. Of area A between a thermic deposit which is in temperature Tn. This is the thermal deposit is at the temperature Tc and the temperature of the bar is Tm. Then let's suppose that Tn is bigger than Tc, so the temperature of the bar is bigger than the temperature of the thermal deposit. The heat transference through the bar, from the bar, there's going to be heat transfer from the bar towards its environment, which in this case is the thermal deposit, in order to reach equilibrium. This is a very important, it was a very important word for the chapter. So in order to reach equilibrium, this is going to be given by this formula. We know that the power is equal to Q over T, and this is going to Tn minus Tc over R, where R is the thermal resistance of the bar. So the chapter ended there, but we can summarize this whole thing into a series of concepts which are very important for this chapter, who were very important for the chapter. And those were, first, it was heat. This was all based on heat. Then energy. Then it was also temperature. All these are applied in a change because we have two objects, two systems that are different in either heat, energy, or temperature, and there's going to be flow of energy between both. And this is all summarized in order to reach equilibrium. So as long as you understand these concepts and the main concepts about transference of heat and energy between objects and systems, this chapter was about that, and the first law of thermodynamics, which state that the change in internal energy of isolated system, this means that there is no influence on this, is equal to the heat that flows from the system to the environment minus the work, no, the heat flowing from the environment to the system minus the work done by the system towards the environment. And well, that's all. I hope you like it, and I hope I help you.